Last video, the law of large numbers. Divide a sum of independent, identically distributed variables by n, and the empirical average settles onto the mean. The fluctuations vanish. This video zooms in. Divide by the square root of n instead, and the fluctuations do not vanish. They stabilize into a definite shape. First, the central limit theorem, what that shape is, and why the starting distribution does not matter. Then the intuition built through the moment-generating function where sums become products. And finally, the payoff, the normal approximation, which estimates any large sum with a single table. When we first met the Gaussian, we promised that many small independent effects would explain it. This is where the promise is kept. Here is the statement. Take independent, identically distributed random variables with mean e of x and variance sigma squared and form the sum Sn. Center the sum by subtracting n times the mean and scale it by sigma times the square root of n. This standardized sum has mean 0 and variance 1 for every n. The centering removes the drift. The root n scaling holds the spread steady. The central limit theorem says, as n grows, the probability that the standardized sum lands at or below any x converges to the integral of the standard Gaussian density up to x. The standardized sum converges in distribution, the very notion we defined for CDFs, to a standard normal random variable. Now here, what the theorem does not ask. It does not ask where you start. Begin with a flat distribution or a lopsided one, standardize the sum, and the limit is the same standard normal every time. Only the mean and the variance survive. Every other detail of the starting distribution is forgotten in the limit. That is why the Gaussian is everywhere. It is the shape large sums cannot avoid. One case we can check completely. Suppose every xi is itself Gaussian, with mean m and variance sigma squared, drawn fresh and independent every time. No limits yet? Just bookkeeping we already own. When we convolve densities, we learned that sums of independent Gaussians stay Gaussian. So Sn minus nm over the square root of n is Gaussian for every n. Compute its mean, the centering makes it 0. Compute its variance. The n independent variances add to n sigma squared, and dividing by root n divides the variance by n. What remains is sigma squared with no n anywhere in sight. So for Gaussian inputs, the scaled sum does not merely converge. It is the same distribution at every single n. The curve never moves. This is the invariant sequence we met when we defined convergence in distribution, and the central limit theorem is the claim that every finite variance input flows to the shape the Gaussian already occupies. How do you build the intuition that every distribution flows to the same limit? Not through the density, through the transform. Assume the mean is 0 and the variance is 1. Proper scaling recovers the general case. Assume, too, that the moment-generating function of x exists and is finite. Our tool is its logarithm, capital lambda of s, the log of the expectation of e to the sx. 3 numbers pin this curve near the origin. At 0, lambda is the log of 1, 0. Its first derivative at 0 is the mean, 0. Its second derivative at 0 is the second moment, 1. Near the origin, lambda hugs the parabola s squared over 2, and that is the whole secret. Now bring in the sum. Independence means the expectation of a product factors, the generating function move we have used twice before. The log MGF of Sn over root n collapses into n identical factors, n times lambda of s over root n. One function of one variable controls the entire sum. What happens as n grows? Write it as lambda over 1 over n and apply L'Hopital's rule twice. Each pass peels one derivative off lambda until the second derivative at 0, which is 1, stands exposed. The limit is s squared over 2. Watch it happen. As n grows, the curves settle onto the parabola, so the MGF of the scaled sum converges pointwise to e to the s squared over 2, precisely the moment-generating function of a standard normal. That pointwise convergence of MGFs forces convergence in distribution, a sophisticated result we state without proof. The theorem earns its keep as a calculator. Take any large IID sum, n is large, and the mean and variance are known. The CDF of Sn at x is the probability that Sn is at most x. Standardize both sides of the inequality, and the left side is, by the theorem, approximately a standard normal. So the CDF of the sum is approximately capital phi, the standard normal CDF, evaluated at x minus n times the mean over sigma root n. One table of phi serves every large sum with finite variance. A concrete run. A transmitter sends 100 bits, each equally likely to be 0 or 1, independently. What is the probability that at most 55 are 1s? The mean count is 50. Sigma root n is 5. Standardize 55 minus 50 over 5 is 1. The answer is approximately phi of 1. The area under the standard Gaussian density up to 1, about 0.84. The key idea of this video, a large sum, scaled by 1 over root n, forgets its distribution. Standardized, it flows to the standard normal. We opened with sets, we close with the bell curve, probability, end to end.